As an essential raw material from the 19th century until today, oil has greatly contributed to the development of chemicals, new products, and new technologies. But its depletion and its carbon footprint are questioning its use. Global warming is now, more than ever, a public matter. The ecological awareness to consume and produce differently is underway, especially in the materials sector. Lately, the composite sector renewed its interest in plant fibers as a substitute to petroleum-based materials. Did you know that 17 companies and research institutions were working on the development of bio-based materials in a project named SSUCHY? Thanks to EU funding, they have worked for 4 years to develop bio-based composites, with advanced functionalities demonstrated through several industrial products. Discover SSUCHY project's 4 main challenges. Challenge 1. How to develop a hemp-based competitive reinforcement? Hemp is a notable and sustainable source of natural fibers that can be used for composite applications. What are the advantages of hemp? It's an environmentally friendly and fast-growing annual crop. It has a CO2 absorption capacity of around 1.5 tons of CO2 per ton of hemp. It requires limited amounts of water to be produced. It can be grown without herbicides, pesticides or fungicides. It regenerates and improves the quality of soils. It has a low need of fertilizers and manpower for farming. It constitutes an interesting alternative to carbon-based and synthetic fibers by saving much more energy cost production. In Europe, hemp is currently processed using mechanical systems, such as hammer mills, known as decorticators. It provides short and medium-length fibers from disordered straws. This processing method is quite damaging for the fibers, and the tensile properties are generally lower than for flax.
Donc dans le cadre du projet SSUCHY, nous avons étudié 2 voies de production de renfort continu alignées à partir de variétés sélectionnées, à savoir Futura 75 et Fibror 79, cultivées et traitées en Italie et en France, en utilisant des conditions agronomiques de rouissage et de traitement optimisés.
Route 1 follows the traditional method to obtain long fiber flax, including the use of the flax machinery. It requires the use of aligned straws and the scutching and hackling machines dedicated to flax. The process parameters were successfully adjusted for hemp stems to obtain high-performance fibers combined with high long fiber yields. Route 2 uses a more economical method, in which the most important processing tools are breaking rollers and the carding process. The main advantage is that it doesn't require aligned stems. Hemp can therefore be processed using traditional equipment for processing hay by a combine machine, commonly used in France and Europe.
Dans les 2 cas, des mèches à faible torsion idéales pour le tissage ont été obtenues. Les résultats montrent qu'en utilisant les 2 voies, le chanvre peut atteindre des propriétés comparables aux fibres longues de lin de haute qualité pour les composites à haute performance. Ces étapes de traitement primaire ont été démontrées à l'échelle laboratoire, mais aussi en utilisant des machines industrielles.
SSUCHY demonstrated the weavability at both lab and industrial scales using the low-twisted roving-type yarns. Using roving-type yarns instead of twisted yarns makes a significant difference compared to the traditional processing for textile application. It lessens time, energy, and money consumption.
Une très grande variété de renforts 100% chanvre pour des applications composites a été ensuite produite à l'échelle laboratoire et industrielle, avec notamment des tissus équilibrés et non équilibrés et différents schémas de tissage tels que le satin, sergé ou la toile. Également des tissus quasi unidirectionnels et des préformes tressées.
The partners also produced and optimized commingled rovings and hybrid fabrics, mixing hemp and bio-based polymeric filaments, such as PA11. They have the main advantage of containing both the reinforcements and the matrix. They offer reduced processing time, consistent with automotive production constraints, fast, clean and automated manufacturing, infinite shelf life compared to thermoset prepregs, and recycling possibility. Challenge 2. How to elaborate bio-based functionalized and optimized polymers. An important part of plant fiber composites is the matrix, which provides a barrier against adverse environments, a protection from mechanical abrasion, and a transfer of load to the fibers. Polymeric matrices are the most commonly used in plant fiber composites. They are lightweight and can be processed at low temperature. Most of the matrices currently used are produced from non-renewable resources. Therefore, the resulting composite materials are not environmentally friendly, which means the development of fully bio-based polymers is an important issue.
Différentes sources de biomasse, en particulier des écorces, appelées ANA, de bouleau, de pin et de chanvre, ont été traitées par fractionnement catalytique pour obtenir des composés monophénoliques et les convertir ensuite en monomères et polymères à l'aide de procédés de chimie verte. Des procédés efficaces ont été mis au point au moyen de l'analyse du cycle de vie. Une bibliothèque de monomères a ensuite été évaluée pour des applications de polymères. Les polymères sont généralement séparés en deux classes, les polymères thermoplastiques et les polymères thermodurcissables. La principale différence entre eux est la réaction du polymère à la chaleur.
When the thermoplastic polymer is heated, it melts, softens, and can be reformed when cooled, and can be easily recycled. However, most of the bio-based thermoplastic polymers commercialized are not rigid enough at service temperature. So, we produced, using tandem catalysis, a library of bio-based thermoplastic aliphatic polyesters. They have increased thermomechanical properties, while retaining recyclability and biodegradability. The main advantages of this method are: no side products are formed, no purification of intermediates is necessary. Unfortunately, upscaling the production of the most promising ones was not successful. Therefore, the production of fully bio-based thermoplastic polymers remains a main challenge to be recyclable, suitable for plant fiber composites, and applied to the transportation sector.
A l'inverse, lorsqu'un polymère thermodurcissable est chauffé, il durcit, ne peut pas être retransformé et reste dur lorsqu'il est refroidi. Ainsi, même s'ils ne sont ni recyclables ni biodégradables, des polymères époxy thermodurcissables entièrement biosourcés ont été développés au sein de SSUCHY pour répondre aux exigences thermomécaniques difficiles des applications visées. En fin de vie, ces matériaux peuvent être avantageusement incinérés pour produire de l'énergie.
Nowadays, the diglycidyl ether of bisphenol A is the most commercially used. But a major drawback is that it contains bisphenol A, an oil-derived substance, and an endocrine disruptor. Within the SSUCHY project, we elaborated two epoxy resins from the biomass-derived monomers, named bioeconomy and bisguaiacol. They were polymerized with bio-based acid anhydride hardeners to obtain fully bio-based epoxy polymers.
BBI est une résine époxy entièrement biosourcée, dérivée de l'isoeugénol. Elle respecte les spécifications du démonstrateur SSUCHY en matière de propriétés thermiques, mécaniques et de résistance au feu, et ce même jusqu'au stade du composite. La principale limite rencontrée a été la mise à l'échelle de sa production. Ainsi, un autre polymère époxy, entièrement biosourcé et non toxique, a été développé à partir d'une chaîne de valeur durable et économiquement viable. Il est basé sur un monomère époxy non nocif, l'éthylguaiacol, dérivé d'une matière première abondante, renouvelable et sous-valorisée qui est l'écorce de bois.
Ethyl guaiacol can be transformed by green chemistry to bisguaiacol. The fully bio-based epoxy polymer has thermomechanical properties equal or superior to the widespread DGEBA-based epoxy, and it has a very good affinity with hemp fibers. We used it for the development of hemp reinforcements. That's how we obtained fully bio-based, environmentally friendly, and non-toxic composites. Their mechanical performance is comparable to glass fiber reinforced DGEBA-based epoxy composites. Challenge 3. Can we implement new functionalities into multifunctional bio-based composites? We still need fully optimized plant fiber composites for structural applications and high added value products. There are indeed remaining technological and scientific barriers to be knocked down. The improvement of their durability, in particular the moisture resistance, the refinement of predictive models, and the development of robust design methods, taking into account the specificities of such materials.
In SSUCHY, different fundamental aspects were studied to better understand and also to improve the durability of plant fiber composites. We proved that durability of natural fiber composites is enhanced when manufactured at equilibrium moisture content of their targeted application, or in general by not drying the fibers. Polymer matrices and composite processing can be adapted to allow processing with damp fibers. One of the main results and illustration here is the development and commercialization of cobalt-free unsaturated polyester resin accelerators to allow processing with damp fibers. The fiber matrix interface can also be improved to slow down water uptake and to allow processing with damp fibers. Surprisingly, long-term moisture cycling improves the properties of the plant fiber composites, leading to speculation about fiber strengthening mechanisms like hornification or self-healing. Water immersion testing best simulates the natural aging tests for uncoated composite samples. A large database and models were created to predict long-term behavior of plant fiber composites and sandwiches under varying hydrothermal conditions. The fatigue behavior and durability of these materials were characterized in view of automotive and aerospace applications.
Sensitivity to moisture is specific to plant fibers compared to traditional glass and carbon fibers. Damping capacity is another one. The use of plant fibers' damping capacity within a composite is still not sufficiently valorized in vibroacoustic control to mitigate resonance. So, at SSUCHY, we also put an emphasis on the damping behavior of lightweight bio-based composite and sandwich materials for applications in the transportation and acoustic sectors.
L'objectif principal était de comprendre le comportement des matériaux composites biosourcés en termes de vibration et d'acoustique afin de concevoir et de fabriquer des structures avec des propriétés d'amortissement et d'absorption importantes, sans détérioration des propriétés fonctionnelles comme le comportement statique, le fluage, la résistance à la température, la résistance au feu.
Indeed, traditional composite materials are often used for their excellent performance in terms of weight and stiffness. However, they have a downside: poor damping properties. In comparison with petroleum-based composites, we observed much higher dissipation properties induced by plant fibers embedded in composites. All the fundamental knowledge collected with SSUCHY was used to significantly improve the damping level and the vibroacoustic behavior of products, like high-end loudspeakers. We also investigated other advanced functionalities, such as fire retardancy, with the synthesis of a new efficient bio-based flame retardant derived from eugenol and acting as a copolymer, with a better understanding of the behavior of an existing and commercialized thermoset furan resin, derived from sugarcane with natural fire retardant properties, and with the optimization of the materials manufacturing with the SSUCHY hemp fabrics pre-impregnated with the furan resin. Challenge 4. How to demonstrate the application of the new, fully bio-based composites into 4 industrial demonstrators. The fully bio-based composites with improved functionalities from SSUCHY were used to develop demonstrators for 4 sectors: aeronautics, audio, automotive, and transportation. The first application sector is automotive, with the development of hemp-based trunk load floor.
Des panneaux sandwich biosourcés composés de peaux en tissé de chanvre et d'une âme biosourcée, tels que du balsa, du nid d'abeille papier alvéolaire et de la mousse PET recyclée, ont été développés pour remplacer la solution pétrosourcée BPREG classique, composée de fibres de verre et de résine polyuréthane, dans les panneaux sandwich utilisés pour les pièces semi-structurelles, telles que des planchers de coffre ou des tablettes.
The main requirements to fulfill were static and creep behavior at temperatures up to 90 degrees Celsius and humidity up to 95%, static punching properties, and vibration damping properties. Some of the proposed solutions allow mass saving at laboratory scale and a reduction of carbon emission both during the production phase and the service life. The main obstacles to reach mass production are mainly related to production rates and the economic competitiveness of the bio-based solutions.
Le deuxième secteur d'application des matériaux biosourcés développés est l'aviation, avec la réalisation de pièces intérieures d'un avion électrique et plus particulièrement un tableau de bord.
The main requirements to fulfill the aircraft specification and certification rules are mechanical properties with skin core adhesion, flexural strength and impact resistance, acoustical properties, environmental compliance including vibration, humidity, gas/vapor emissions, weight, and the fire retardant performances, all evaluated and validated through 4 tests according to the EASA regulations.
SSUCHY a proposé de remplacer les solutions carbone-époxy de conception actuelle par des matériaux sandwich composites renforcés par du chanvre. 2 démonstrateurs ont été conçus en utilisant des règles de dimensionnement aéronautique et produits en utilisant des sandwichs composites époxy renforcés par du tissu de chanvre et du flax tape. Une amélioration significative de l'amortissement des vibrations a été observée par rapport à la solution réalisée avec du carbone. Le principal défi à relever est l'obtention
d'une solution entièrement biosourcée avec les propriétés ignifuges attendues.
As a second demonstrator in the transportation sector, a bio-based scooter body from the Eco electric scooter was also originally developed using hemp reinforcement. The concept of the electric scooter is a large monocoque structure to which the drivetrain, a large battery pack, the steering construction, the saddle, lights, etc. are added. The function of this monocoque is to add all parts together in order to have a functioning product. The scooter is a perfect case for testing and demonstrating use of high-end biocomposites in mobility applications. In the SSUCHY project, the monocoque was redesigned and optimized to increase the bio-based content from 30 to 65%, save mass by approximately 55% and decrease the expected labor time to 50%. The optimized design was implemented in a prototype as a proof of principle made of woven hemp fabric and cork.
The fourth application targeted within SSUCHY is the high-end acoustic sector. We developed a green loudspeaker whose structural part is a monocoque cabinet component. It is initially made using RTM with a U-shaped cross-section made of carbon fibers, glass fibers, epoxy matrix and PU foam. The main requirements are linked to the vibroacoustic behavior, the production cycle time, the recyclability, sustainability and costs. The solutions we successfully proposed are composite loudspeaker systems made with different bio-based and eco-friendly materials. The loudspeakers are made with hemp and flax woven fabrics, cork and recycled PET foam. The natural damping capacity of plant fibers gives the system excellent dynamics and vibroacoustic performances.